Uh, yeah, I don't. He has one very, very vivid childhood memory about um, um, which really stands out. She mentions it every Christmas. She and her and I, we built a snow hut igloo, not a fancy one, but it was here in Copenhagen. I'm native from here, and every year she mentions that. Every time there's a little bit of snow, she mentions that story about her and I building that super simple snow hut. Took a few hours, probably took half a day, I don't remember. But she really remembers that stuff. I remember, I'm older, of course I am, I'm his father. I remember building quite a few snow huts during my time. Probably a handful or more, and but she only had that one memory. Um, There's no doubt about climate change is here and is something that's happening. And I guess you are all here in this presentation because you believe in that stuff and you want to do something about it. You're passionate about I don't know, saving an environment, doing your thing, and that's why I'm here. That's why I'm standing on this stage today, and that's what the project and the solution I built together with the team and I are talking about today. Um, I hope this is going to be a little bit of an interactive session, so please do ask questions. Actually, I have a team member of mine sitting over here, Tess, over in the corner, who actually built a lot of this stuff. I just talk about it. So, all right. So that leads me to the real start of the presentation. Last summer, actually in August last summer, the team and I started working for the most sustainable energy company in the world. They were awarded that in 22 and 23. Um, and they wanted us to build a screen supercomputer that could help them optimize their products. And their products are wind turbines. But they had a little curly at the end of that building a supercomputer. They wanted to do it as green as possible, meaning as low carbon as possible. Of course, there's a lot of other requirements, but what I will be focused on this presentation is about how we made it as green as possible, and also a little bit on cost because it might incur a little bit of cost. Cool. So Vestas, the challenge that we were facing is that we needed to execute what is called a wind turbine simulator. Yeah, the word says it all. It's about simulating turbines. Like instead of building a massive amount of turbines, you can simulate with I don't know, AI, ML, whatever. Pick your choice of weapon here. And there was two things they wanted to get out of these simulations, and it was optimal placement of turbines in a wind farm, meaning if you erect 100 turbines, how are they supposed to be located within that area to get the most amount of energy out of a turbine? The other one was structural optimization, which was actually the biggest part for what we did, but it doesn't really matter. And that's if you build a turbine and the same turbine you erected in the North Sea versus somewhere in central Germany, there's a huge difference about the wind forces that will actually experience. In the North Sea, there will be huge wind gusts. In Central Europe, somewhere, if you erect the same turbine, it's not going to be much. It's going to be, I don't know, 20 meters a second. That's probably the max wind gust you'll get. But in the North Sea, it can easily be, I don't know, 50 or 60, whatever, a high number. So that's what we did. That's what these calculations did. The structural optimizations meant that on a single turbine, they can save up to 50 tons of material. Consider just the tower of the turbine. They can actually make the tower steel thickness thinner if they placed it down there. And that's what we did. So saving 50 tons of material is quite a bit. I'm amazed by the turbine they built. This is the newest one. It's called V236, I think it is. And this is the nacelle, it's called, that is the photo of here, transporting on a road in Denmark. It's basically the house they put on top of the tower. And that nacelle is where the generator is located. And that one weighs 880 tons. Huge amount. And imagine that you need to place that on top of a tower the tower that specific one was erected on was 150 meters tall. And then they attached the blades, and the diameter of the blades was 236 meters. Hence, it's called 236. It's massive. You can actually go to Østerild and see it. I was there when the first kilowatt of hour were produced in December 27th last year. It's quite amazing. Fun story. I'm a software developer. I saw software engineers basically hooking up to the turbine and debugging it while I was there. It's kind of interesting to see you can do that stuff like that. Of course you can. There's a lot of software. That single turbine produces 15 megawatts of power, which is equivalent to the 20,000 standard European households for just one turbine. But the numbers are just staggering, and I'm glad I helped it a little bit. My team helped build a little bit about these turbines. So it's, yeah, another fun story while we're here. I tried to take my own photo of that turbine with my camera and stuff, but I couldn't really because I had to go so far away, so it didn't look impressive at all. Like taking a photo of something that's 280 meters tall, yeah, you need to be quite far away. Cool. So Vestas had these challenges. They had an on-premise HPC cluster, a supercomputer, call it what you want. It was fairly expensive to maintain, and last week it crashed 3 times. I know that because we're still working a little bit with them. Vestas expects, or the entire industry expects, to grow with a rate of 300% the next few years. So the amount of calculations they need to do is at least tripled. But why I said at least is that this turbine is many times more complex than any of the other turbines they built before. So it's the amount of computational power they needed to do these calculations was enormous. So if we look at executive high-level requirement distilled down to what I'm talking about today, don't look at all the functional requirements. It's just, this is what we're talking about today. Huge scale, 400,000 cores. Vestas is not making any money, so it needs to be inexpensive. Of course, 400,000 cores and it's going to be expensive, but as cheap as possible. And then, as Vestas wanted to keep being the most sustainable energy company in the world, as green as possible. So that's what we set out to do. And then we look a little bit inwards toward my industry. I work in the IT industry, and I'm assuming you do too. And that's where it's sort of, if you dig down into the numbers, you realize that our industry emits almost twice as much CO2 emissions than the aviation industry does. That's a huge amount. I did not know that a year ago. I know that today, and I'm very, very interested in what I can do as a software engineer. And I hope you are interested in figuring out what you guys can do. Right, and I'm going to talk about some of it. I don't have a solution for everything, but I do have a lot of solutions. All right, so let's jump right into it. There's a foundation called the Green Software Foundation, and a lot of large companies are part of it, including Microsoft, which is my employer. And they have a number of software principles that are grouped into these three groups. So there is energy efficiency, there's hardware efficiency, and then carbon awareness. And I'm going to talk more about each of them. But the first one I'm going to talk about is energy efficiency. And it is about software performance in general. It's about choosing an efficient programming language, for instance. And I know that there's a few Python lovers here in the room, so I have to show a slide just to provoke you a little bit, just for fun. So I'll show this one. And this is a study that came out, I can't remember, eight months ago or so, how efficient each language were. And if you look at C versus Python, it's 75 times more efficient. You can't really use this for anything, but you can toy and make fun of all your Python friends. That's what I use it for. I'm not a Python developer. But what you should be looking for in efficiency here, in my opinion, if you run 400,000 cores with Python, yes, you're gonna get a huge benefit of changing to another language. But most application you're building, it doesn't matter. Optimize for developers, optimize for delivery instead, in my opinion. So, then there is hardware efficiency, like figuring out what hardware you're running on. There's a huge difference in what kind of hardware you're running. It could be your virtual machine is too big, or your machine is too big and never really utilize more than 30%. Again, I can mention what we do here at Microsoft. Is that if you spin up a virtual machine and it's not very utilized, the Azure advisor will tell you, please take a look at this one. Why is it never CPU utilizing over 30%, for instance? You can also choose much more efficient CPU architectures. Like we think of ARM being something that's in a tablet or in a phone, but it's actually coming to servers, and it's a lot more efficient than Intel-based CPUs. It doesn't have all the legacy, so like you can easily just by switching to an ARM processor, depending on your thing, probably saves 70% carbon emissions just for the electricity consumption. And of course, you can turn off unused resources. Like, do you really need 7 web servers during the night when everybody is sleeping and you're running the Danish broadcasting television site? No, you probably don't. You can turn it off during the night and turn it on in the morning and stuff like that. Then there is carbon awareness, and that's where we did all of this, and I'm going to walk through what we did with Vestas. But carbon awareness is figuring out when or where does your workload need to run. Like, can you postpone something to run at night, for instance? Like people suddenly started doing under the war in Ukraine versus Russia, and electricity prices suddenly skyrocketed. Everybody figured out, oh, I have a timer on my washing machine and a dishwasher and stuff, and started at night. You can do the same thing with your compute processes. And this is software. You can also move it around in the world where it's greenest, for instance. So these two functionalities called time shifting and location shifting. Cool. Then there's a lot of layers here we need to look at, and the next layer is sort of the data center. When you look at a data center, for instance, there's something called PUE or power usage effectiveness. And if you look at a data center, a random data center, and it consumes, well, the meter says you consume 15 kilowatt of hours. It's not uncommon to see that 10 kilowatts of those actually goes into the servers, and the rest goes to cooling and the PUE. Hence, so you have a third waste of electricity used just used for cooling. Hence, the PUE is 1.5. The hyperscale data center is normally around 1.2, but there are data centers you see where the number is more than 2. Older data centers. But 1.5 is actually where the sweet spot for most data centers is located around the world. And again, the hyperscale data centers try to optimize this as much as possible. Actually, this number is fairly difficult to get from any of the providers because they don't trust you with the value. And that has to do with, if you compare 2 data centers, you can't just compare them. If you take a data center in northern, let's say, Finland versus one that's running in Singapore, it's way easier to cool the data center in northern Finland compared to Singapore, where it's humid, hot all the year round. So you might get as low as 1.1 PUE in Finland, but you'll never get below 1.4 in Singapore. So you can't just compare them like that, but you can of course move your workload if it makes sense to Finland. So you can get these numbers, it's fairly difficult. Cool. So what we did to start our journey here with Vestas is we had these workloads. We had a defined number of workloads we needed to run. So we needed to make it as efficient as possible and as cheap as possible. So we looked at, so that's why I have the piggyback here, what was that, piggy bank and a tree. So that sort of symbolizes where did we actually save a little bit of money and where did we actually make the solution more green. So what we did was, it was very CPU or compute heavy processes, so we need to saturate the CPU. So there's no real delay or wait for anything. So that's what we did. So we figured out which CPU architecture was the most efficient for this workload, and made sure that we never really waited for disks. There's a lot of data involved in this system, and both of them actually made a lot of financial sense, and also environmentally sense, because choosing the most efficient one, so we didn't have a CPU waiting every other second for data that needed from the disk I/O. The same thing we did actually with the virtual machines. It's quite easy cloud data centers to try out a handful of different virtual machines. We didn't try out that many because we really figured out which one was the optimal one for our workloads, and that was, I can't remember, it was DSV3, I think we ended up with that SKU. And then the auto scaling up and down, like removing resources that we didn't really need. Of course, the system had an API and a web page where we ran a minimum of one web server. I actually think we did 2 for redundancy, which we couldn't really turn off because we never knew when they were going to submit a new job. But the cluster with these 400,000 cores, we could scale to 400,000 cores and to 0 fairly quickly. We're talking minutes, not hours, and vice versa if we wanted to. So there's no doubt about that there was a huge cost saving, so they didn't have to pre-provision 400,000 cores running, and in the weekend there's going to be used nothing, but we can rescale it down to nothing, and hence we won't consuming that amount of energy. And yeah, Vestas saved a lot of money. Then we also, the cloud providers have, if you make a contract, if Lego, for instance, make a contract with any of the cloud providers, say we need 10,000 virtual machines, and then they have to guarantee that these 10,000 virtual machines are available. But that's not very efficient. Like they're just sitting there idle, probably turned off. But in Azure, for instance, or other cloud providers, in Azure it's called spot instances. You can borrow virtual machines that are reserved from others that they don't use, and you can get up to at least 70%, 80, or even up to 90% discount on these virtual machines. So we obviously saved a huge amount of money by running on spot instances, and we also saved quite a bit of carbon emissions by not producing additional 10,000 virtual machines. There's a caveat with using spot instances, for instance, is that if Lego, in this case, suddenly decides they want to start their virtual machines, they will be reclaimed and you have 30 seconds to save your work. So there's a risk of you losing your work. Luckily for us, whatever we did was super small computation. It took around 3 minutes on the virtual machine and the CPU architecture we chose. So in reality, if they took out a virtual machine with 16 cores, we could lose up to 16 times 3 minutes. Or if they took all of them, there's of course a lot more. But luckily that doesn't happen that much. So it wasn't really a huge problem for us. So let's talk about carbon awareness. And you know carbon. Carbon is carbon dioxide. And that's the formula for carbon dioxide. But carbon dioxide is not just carbon dioxide. It's actually, when we talk about carbon and carbon awareness and carbon emissions, we actually mean carbon dioxide equivalents. And what the heck is that? Like equivalent meaning there are other greenhouse gases than carbon. There's, for instance, methane. And keep carbon equivalence, carbon dioxide equivalence is a metric measure of how to compare emissions of various greenhouse gases. For instance, is something called global warming potential, meaning if you take methane, like what you use for your barbecue, but basically gas or whatever comes out of cow and you for that matter, the global warming potential is 25 for methane versus 1 for carbon or carbon dioxide, meaning it's 25 more dangerous to do, for instance, the ozone layer or building this, what's that called? Rock around the earth to carpet around the earth to heat the earth. And if you look at nitrous oxide is 298 times more potent than carbon and carbon dioxide. Hence, if you emit 1 gram of methane, which is 25 times more, it's equivalent to emitting 25 grams of CO2. And that's what we talk about carbon dioxide equivalence. But in normal words, in articles, and everywhere, we just talk about carbon. So yeah, now you know. And when you talk about carbon, we also have another term called carbon intensity. And it was even in the title of this talk, and I thought maybe I should remove it because most people don't know what it is. But carbon intensity is carbon dioxide equivalents per kilowatt hour produced. So how many grams of CO2 does it require to produce a kilowatt hour of electricity? So that's it. So if you look at electricity production worldwide, how it's combined out of different sources like nuclear, coal, wind, solar, whatever they use, geothermal. This mix is called electricity mix, and an electricity mix. If you look over the period of the last, from 2010 to 2020, that's the only data I actually could find. You see the amount of coal being used going down in the right direction, and it's going further and further down. So, and you see the renewables energy going up. And so in 2020, 25% of the energy produced in the world was actually renewable, which is a good story. And if you look at coal, it's actually going down. But that's not the right image, because this is the percentage. The problem is that we consume a lot more energy. So our energy consumption has more than doubled, actually a lot more. And if you look at the latest numbers I could find in this graph was up to 2021, you see that renewable energies such as bioenergy, solar and wind are actually increasing quite dramatically, but so is coal. And the electricity mix becomes important when you sort of figure out when my workload is supposed to be running. Because then you need to get these data over time, because it changes. For instance, if you take Denmark right now, it's not much sun, a little bit of wind, I guess. So if the right column here, left column, sorry, is point in time, right? For instance, right now, it looks like we have a demand, which is the top bar, and most is actually produced by solar or wind. That could be right now, and a little bit is produced by coal and gas here in Denmark, for instance. But later tonight, if you move to the right this time, bar, where the sun has got down and the wind has settled a little bit, and assuming we have the same demand, in that case we'll use a lot more gas and oil, and you can actually see this 120 on the left side. The 120 is the carbon intensity, meaning at that point it required 120 grams of carbon emissions of carbon to produce a kilowatt hour. But tonight at 8 o'clock, for instance, if that's the case, it's at 350. So this thing changes a lot over time. And I'll show you in a second. You can actually look at live data if you want to. I will do that, by the way. But so if you draw this graph a little bit differently, or you can see over a period of time. So instead of starting your workload here at, let's see how this one works, at this point, move it an hour and 23 minutes in where the carbon intensity is low, and if you know how long your process is going to take, you can move it there and start it, and then you save a huge amount of carbon, depending on how the values of the curve. And in our case, we worked with two data centers, or two Azure regions. There's one called Western Europe, which is in the Netherlands, and there's one called Sweden Central, which is in Sweden Central. That's two locations. So in the Netherlands, it's right next to Amsterdam, and in south central Sweden, it's right next to Stockholm. And at this point in time, you can see the carbon intensity in the Netherlands is 165 grams per kilowatt hours. And it's mostly produced by renewable energy. So 71% of it is renewable energy. And if you look at Sweden, it's only 22 grams. It's a huge difference here. And it's mostly renewable energy, but all of it is low carbon. Low carbon includes nuclear. But if we try to take a look at this tool, this is a tool called Electricity Map, which is actually a Danish startup, not far from here. So if we go here, oops, that was not my intent. Let's make it a little bit bigger. So if you look at it, this is live data. I put the slider here on live, and you can actually see how each country, what the actual value is. So we hover over the Netherlands, it's 185 right now. If we hover over Sweden Central, it's 23. If we take Denmark is divided into two zones. So here where we are at, right, it's 209. That's the carbon intensity. And we can actually drill deeper into it and see what does that actually consist of. Now I've zoomed quite a bit. So if I go in here, you can see we get quite a bit of power for biomass, a little bit from coal, very little from solar. And this is actually our full capacity in this region. And then quite a bit from solar, which I'm quite surprised about. So that's quite interesting to see that you can actually get these data live, and we actually use this system to actually get these data out to use in our solution. So we needed to figure out how to utilize this carbon intensity. So we started doing time shifting, meaning asking the user, you just submitted a huge job, like it requires 10,000 cores or whatever the value is. Is it okay if we process it later tonight at 8 o'clock? It'll still be available tomorrow at 8 a.m. when you get to work. Yeah, sure. And then we can tell them you saved 17% CO2. So that was a huge amount of saving in carbon emissions, not really any financial savings. And the other thing we did was location shifting, where we used these data and figured out if you run it in Western Europe right now, versus Sweden Central. What was then values? I can't remember. 165 versus 23 right now. So that's roughly saving 65% or whatever my math says, it tells me, just by moving the workload there. Under the assumption that network traffic is free, which is not, but let's ignore that for now. There's one implication here, and that's why the check marker under the piggy bank there is not really white, because it might incur a cost moving it to Sweden versus having it in Western Europe. But yeah, that's a decision that the business had to make. So how do we actually build all this time and location shifting? Cool. And then there's going to be a few hand drawing diagrams here. And if you look at this is part of the system architecture. It's actually covering most of the important stuff, and we're not going to talk about all of it. But the important parts here for us here is that we have two compute clusters. And these small cherries or whatever it is compute cluster. And there's the top one here is Western Europe, and the other one is Sweden Central. So that's where we had the compute running. And over here on the left side, we have something called the DC client. That's the client they used. So which they already used with the existing supercomputer they had on premise. So we didn't really change that, except it talked to an API. So that's the API we built. So when you submit a job, the DC client dumps a number of files, the executables and whatever DLLs and configuration settings and stuff like onto a file share we call artifact storage. This is not much data, 10, 15 megabytes, that's it. Quite a bit for input, but that's it. And then we submitted the workload to the API, and the API didn't do much. It could ask you whether or not you want to, when you want the data to be computed, but it's not part of this diagram. But it basically updates the state store in the bottom called AC tables, and then it submits a message to a queue. Nothing fancy, that's all it did. But over on this other side, we have the dispatcher, and that's where all the logic was built in. That was more than half of the entire solution, or the logic or business logic was built into this dispatcher. The dispatcher, in this case, is an Azure function, nothing fancy. But the dispatcher picked up this message, talked to the artifact storage, figured out, okay, how long will it actually take to compute? How many tasks are there? We knew so roughly how long a task would take, and how much compute do we need? Then it would talk the arrow up, talk to the cost API and CO2 API, electricity map, for instance, and figure out where is the optimal place location. And when it did that, it'll, in our case, realize that Sweden was the optimal place to locate it and send the job there. Actually, it'll copy files over there first because that's might be in a different region, as another part of the world, and then it'll submit the job and it'll start computing. And then it'll update the state store. Nothing fancy there. If we didn't have any compute availability or the cluster wasn't started, and it'll take a while before the cluster is ready, we'll actually just push back the message to the queue and try again. Cool. And whenever the job was done, before the job is done, because the job could take hours and hours, perhaps even days in some cases. But whenever there's when one of the tasks was done, we got a notification that, yeah, this task is done and we're actually ready. So we started via a trigger to copy the files back to the user. And there's a lot of files and a lot of data, so it could actually take quite a while to copy millions and millions of files back. So that's what we did until eventually the dispatcher will figure out, get a notification, the entire job is done, and then update the state store. So what we learned while doing all this stuff is that doing time shifting within a day, meaning it had to be done within 24 hours, could actually lower the carbon emissions by 12 to 16%. That's quite nice, just by doing time shifting. You're like, do you want to run it now? No, on average, 12 to 16%. But location shifting, which was a lot more complex to implement, was 30 to 90%. We only did it within EU, but moving compute from Western Europe, meaning Amsterdam to Stockholm, could, in our case today, with my head math, it was like 65% reduction in CO2. So that's quite nice. And it wasn't a huge amount of work. Azure doesn't have a solution for it, neither does any of the other cloud providers. I hope it will come. But we actually built some of the tools for this to actually work. And we did that together with the Green Software Foundation. And to be able to, and I'll get back to the tools in a second, but I just want to figure out how you actually can measure this stuff in your own system today. So, but if you want to improve it, you gotta, I think it's Albert Einstein that sort of said that you can't measure what what you can't measure, you can't improve. I think he said it a little bit differently, but it doesn't really matter. So I've taken an example here and I tried to make it as simple as possible. So I've just took a random Dell server, which is quite popular, in data centers today. It's a 3 gigahertz server with half a terabyte disk and 16 megabytes of RAM. That's more than enough to run my homepage, for instance, and a lot of other stuff. But that's not a fairly common server. And I wanted to calculate the carbon emissions for 1 hour. So how do I do that? And I use something from the Green Software Foundation. I use something called software carbon intensity specification. So I call it calculation because this is not really the specification. So the server is a 400 watt server, and I want to work in per hour. So that means it consumes 0.4 kilowatt hour within an hour. And the embodied carbon, and I need to explain what the embodied carbon is. The carbon used to produce all the components and transfer it to Europe. That's the embodied carbon, is roughly around 1,000 kilos for this Dell server. You can actually look it up on Dell's site, but it's not very easy to see. They sort of give you percentages and stuff like that. So I ended up figuring out it was 1,000 kilos, just also to make the calculation simpler. And we expect this server to have a lifespan of 4 years. So the carbon used to run that server for 1 day is 1,000 kilos divided by 4 years, 365, and 24 hours a day, and it ends up being 28 grams of carbon emissions per hour. Yeah, and let's assume that the carbon intensity right now is 216 in Denmark. I can't remember what, we looked it up before, but it's not far from this. And to make the calculation a little more interesting, because the specification actually has it, we added the number of orders produced, because we want a functional unit to actually represent how efficient we used this actual server. But I'll get back to that in a second. We ignore everything like cooling, networking, anything like that, but we generally just look at that server. Otherwise it becomes, and we don't share it with anybody else. It's just my server. It's not 2 systems running on it, because then the calculation becomes a lot more difficult. So the software carbon intensity specification has this formula. So let me walk through it. So we have the energy consumed in software in kilowatt hours, right? So that's basically what we put into the server at that one. So you can add a meter in front of the server and actually read that value if you want to. That's the most precise way you can measure that. Then you have the carbon emitted per kilowatt hour of energy. So, and you can see that the CO2/kilowatt hour, that's the carbon intensity. So that was 216 hour in our case right now. And then we have the embedded or emitted carbon emitted throughout the hardware manufacturing, or embedded carbon, it's called. That was the 1,000 kilos. And we want to do that calculation per functional unit. Instead of just having a server and saying it ran for an hour and it consumed, I don't know, 400 watts of electricity, we can use this formula. And it's actually quite clever because it looks at efficiency also. So if you go from 398 orders to 600 orders and your power consumption just increases by a percentage, it's going to be overall a lot more efficient, right? So let's try to do this calculation. So I made it easy for you guys. Added these numbers in here and say, okay, 0.4 kilowatt, carbon intensity is 216. The M embodied carbon is 28 grams. And we had these 398 orders coming into the system in that 1 hour. And again, using our formula, add the numbers. So we have a little bit of math to do, and I'm not very good at math. You saw that earlier, so I've done it for myself. So you realize that the carbon emitted for running that server from electricity use was 86 grams, plus the 28, which was production of the server with a 4-year lifespan. That becomes 114 grams for running this server. For that hour. So that's the electricity used and the carbon emission for producing this server. Just to compare that to something, I drive a Ford Fiesta from 2014. It's called an EcoBoost 100 horsepower, so 3-cylinder, small, tiny car, nothing fancy. Yeah, it's almost 10 years old now. That per kilometer I drive emits 132 grams. So this is not much. So not a huge problem. The only problem is that this server runs 24 hours a day. But to finish this calculation, we need to divide that with 368, so we come up with a number which is easily comparable. So it's 0.31 grams per order, per gram CO2 per order. And that you can use to compare your system when you do optimization. You can, for instance, extend your lifetime of the server, then that number will go down. If you make the code more efficient and more orders, that number will go down. If you lower the carbon intensity by choosing another type of electricity, or I don't know, set up your own turbine or solar cell, that number will go down. Or you choose a more efficient CPU, so it doesn't have to use 400 watts. So you change to an ARM processor, it only requires 260 watts. That number will go down. So there's a lot of things you actually can sort of do in these calculations. All right. Some of the tools we used. So Green Software Foundation has a tool called Carbonware SDK. It has all the built-in features to do time shifting. We committed back, or contributed back, so it can also do all the calculations for us for doing location shifting. And over on the left side, you can see sort of that's how the API looks like, and you can talk to it, and that's what we used. Yeah, and it's available as open source, and you're more than welcome to use it. It actually works fairly well, I would say. But Vestas ran into a problem, or we ran into a problem, because we were noobs at this, and now we know a lot better. But they actually set a challenge for us, right? And the challenge is what I've basically written here on these slides. So that they don't mind paying 5% extra for their system running if the carbon emission reduction was large, let's say 50%. And most of you will probably don't mind either, but if I reverse these numbers, paying 50% extra for a 5% reduction, you probably wouldn't. I wouldn't, to be honest. Maybe, depending on how much money it is. If it's an extra 100 kroners a month, I'll probably do it. But if it's 1,000 kroners, I'll probably not. So that's sort of the challenge. So if you just look at the carbon intensity, like we've done so far, the carbon emitted by a system, that's not going to fly, right? We will always choose the option with the lowest carbon emissions. And that's where we needed to figure out, how do we solve this problem? New problem arising. And so we built our own carbon economy SDK, piggybacked on the same name. So instead of carbon aware SDK, it's the carbon economy SDK. It's also public available and as open source, and the Green Software Foundation are actually currently figuring out how they get into their umbrella organization, but that'll take some time. But and how we used it was actually quite simple. So we have the dispatcher, which you saw before. It was the brain of everything. Instead of calling the electricity map directly, we called the Carbon Economy SDK, which did two things. It called the Carbon Aware SDK and then eventually electricity map to get the carbon intensity of the locations we wanted to run. And then it called the Azure Pricing API and figure out, okay, we want spot instances, the one that Lego did not use, right? And how cheap can we get those? And then based on that, we did a calculation, figure out, okay, cool. Today it's Sweden Central, tomorrow is UK South, or in 5 minutes it's going to be Denmark somewhere, whenever that region opens, and we can actually do that. There's an engineer on my team we actually spent quite a bit of time on figuring out how to do this evaluation. What is more important, carbon versus finance. So we actually, I don't know how many iterations of formulas we went through, but we ended up with this fairly simple one, where it weighted price versus emissions based on a a weight. It's all on the blog, but I'll just show an example here. For instance, if you set the emission weights to 0.25, meaning it's not that important, money is more important to me than carbon. You can see here in this scenario, if you have, if we just take the Sweden, Central, and Western Europe in the top table, you can see the emission rating was, or carbon emissions was 29 versus 100, and the unit price, and then we did the calculation and figured out, okay, the calculated weight, the output of this formula, meant that we're going to end up in Western Europe. But if we change it a little bit with the same values and say the emission weight is 0.75, the output says we should end up in Norway East, because that's where it's the combined weight of green versus finance or cost is where we're going to end up. And then a designer had a little bit of fun. We needed to build an admin UI in front of this. So this is actually not entirely how the system ended up looking, but the designer was very creative, and it was a lot of fun trying to figure out how do we actually present this to the user. How can an admin person, a department head, weight finance versus emissions and stuff like that. That's a little bit of a challenge here. So if you look at these up here, you see that you can weight at the greenness versus, you can have 1 leaf or 3 leaves. The more the more important greenness were for you. And the same we did with finance. And then these are our bills, like showing, okay, how much money are you willing to spend? And to nudge that user a little bit, that's how we set the weight. To nudge that user a little bit, so if they move these sliders, we could change the image on the right. First you had a lot of turbines, and it was green and lush, and then it becomes a little bit more irritating, and then it ends up being a cesspool if you only look at money. So that's how we nudged the user. We also had, which we actually didn't implement it, unfortunately. We wanted to add a little bit of nudging to the user here, because we had all the data. So we could easily calculate, so okay, if you change this slider, just a little thing to the left or to the right or whatever, that would have cost you $1,000 and would have saved 17% CO2 or whatever the value is. And then we had a lot of other knobs and turns here we can sort of turn around and play with here in the bottom. We also showed the actual CO2 reduction, budget spending with trend lines and stuff like that. They had a number of levers here to sort of control how many compute nodes we actually set up. So that might be a queue length and the average execution time of. There's all kinds of weird notifications we added up in this application. But so that was our journey from going from noobs, being introduced to this most sustainable company in the world, wanted to build a supercomputer that was very large, required a lot of compute power and a lot of challenges, and then putting that sort of tag in the end and saying, okay, oh, by the way, it needs to be green, because we want to stay on top of this chart saying we're the most sustainable company, energy company in the world. I hope you got something out of it. For me, this has been a learning journey. It's been a lot of fun. And I try to do my best to sort of help the world. And that's part of why I'm standing here, right? So we need to lower these freaking carbon emissions somehow, right? Because it is somehow, actually, maybe it's my daughter's future, not our future. But it's definitely my responsibility together with yours to sort of do your part. Remember, IT industry emits almost twice as much as the airline industry. And we're putting a lot of ban on traveling with airlines. We're adding extra fees when you travel to the airport, but the amount of metric tons we saved with this solution We don't know yet because it's just about to go into production. Actually, tomorrow. um, it's going to be massive. But yeah, I hope you got some tools to figure out how you can do that too with your solutions. So thank you very much.